Okay, this is the title of the presentation, a dissipation-preserving finite difference model of a nonlinear multidimensional combustion equation. The authors are Adán Serna Reyes, Jorge Macías Diaz, and Luis Alejandro Flores Oropesa. And this is the schedule of our presentation. So I'm going to introduce firstly a continuous model. Then for that continuous model, I'm going to propose some numerical model, and I'm going to derive some numerical properties. And finally, we're going to stop this presentation with some conclusions. Okay, so let's introduce first the continuous model. D is going to represent the number of spatial dimensions, and T is going to represent some fixed time. B is going to be the spatial domain, which, as you can see, it's going to be like a box, a D-dimensional box. And the BT is going to represent the space-time domain. LXQ is going to represent the typical LQ space, the Lebesgue space. So in other words, it's going to represent a set of functions f such that for every t, f with t fixed is going to belong to the LQ space. I'm going to introduce the classical Q norm and also the Euclidean norm for when Q is equal to 2. The mathematical model investigated in this work is going to be given by this partial differential equation subject to this initial condition and Dirichlet boundary conditions. As you can see, this is a parabolic equation. A and f are going to be sufficiently smooth functions, as U0 also is going to represent a sufficiently smooth function. This symbol is going to represent the gradient vector, and this other symbol is actually the divergence. So, as we mentioned here, this is a generalization form of the classical diffusion reaction equation, which, by the way, the first term is going to represent the instantaneous rate of change. The second term is going to represent the diffusion, which is going to be dependent on space. And finally, the last term is going to represent the reaction term. Various particular forms are provided by this partial differential equation. So suppose, for instance, that A is identically equal to 1. If f prime of u takes the form u times 1 minus u, then the resulting model is Fisher's equation from population dynamics. If f prime of u takes on the form u times 1 minus u squared, then the resulting model is going to be the Newell-Whitehead-Siegel equation. If f prime of u is u squared times 1 minus u, then the resulting model is going to be the Seldovich equation, which arises in combustion theory. And finally, if f prime of u is of the form u times 1 minus u times u minus alpha, with alpha between 0 and 1, then the resulting equation is the Nagumo equation. This partial differential equation has associated a Gibbs free energy function, which is given in this form. Gibbs free energy in this case is actually the potential energy, which can be represented in terms of our notation in this form. Okay, moreover, it's easy to see that this function is greater than or equal to 0 for every t whenever f is a non-negative function. This is probably the most important result, theoretical analytical result of this presentation. So we call it the dissipation of energy theorem. So if U satisfies the initial boundary value problem, then the associated Gibbs free energy is dissipated throughout time. So the way to establish this result is by taking the derivatives on both sides of the energy function. So you take the derivative of both terms. So after performing some derivations and some algebraic simplifications, it's easy to see that the derivative of A with respect to t is minus the 2 norm of the partial derivative of u with respect to t squared. And as you can see, this term is less than or equal to 0. Therefore, the energy is dissipated throughout time. Let's propose now a numerical model for the system. So I'm going to introduce some notation. So first of all, for every D, I sub index D is going to be this set, and ID bar is going to be the set ID union 0. We take partitions, regular partitions in space and time with step sizes hi and tau. Okay. The partitions more explicitly are going to be provided by these identities. And we employ the following discrete operators. Well, as you can see, this is an average operator. This is a difference operator with respect to time. This is a difference operator with respect to the ith coordinate. And this is an operator which we're going to employ to approximate the derivative of f with respect to u. So this is our approximation of the gradient vector. And the numerical model to approximate the continuous system is going to be provided by this discrete version, this discrete model. Okay, so notice that this is the way we approximate the partial derivative of u with respect to t. The second term approximates the diffusion term. And finally, this is our approximation for the reaction term. Of course, we're imposing initial conditions and homogeneous Dirichlet boundary conditions also. It's important to mention that this system is a two-step implicit nonlinear model. We are going to establish the existence of solutions using fixed point techniques. The system is quadratically consistent, it's stable, and quadratically convergent. And finally, we're going to check also that this numerical model also preserves the dissipation of energy. Okay. We're going to use this well-known fact about these discrete operators. And we're also going to employ Brouwer's fixed point theorem, which is standard from the literature. Also, for the sake of convenience, we are going to introduce this discrete operator. And this is the theorem on solubility of the discrete model. So suppose that A and F are sufficiently smooth, then under these conditions, then the numerical model is solvable for any set of initial conditions. Now the proof is by induction. So at the first time step, so we know the approximation. So suppose that the approximation for the time k is known, and define this function f in this way. Motivated by Brouwer's fixed point theorem, we take the inner product of f of u with u and try to bound from below. Now here we are going to use various things. So some of them are, for instance, Cauchy-Schwarz inequality, Young's inequality, and the smoothness of both a and f. So bounding from below, we obtain that this inner product is greater than or equal to this term, where lambda is this positive number. Using now Brouwer's fixed point theorem, it follows that there is a solution for this system, and that's going to be the approximation at the time k plus 1. Another important property of this model is that it's able to preserve the dissipation of energy. Suppose that uk is a solution of our system, and define this expression ek, which, as you can see, this is an approximation for the Gibbs free energy. Then the discrete rate of change of the energy is going to be provided by this term. And as you can see, this term is less than or equal to 0, which means that the energy is dissipated. Moreover, in case that f is non-negative, then the energy is also non-negative. Now, the proof uses basically the energy method. So take the inner product of this term, this difference in time, with the finite difference scheme. So since the finite difference scheme is equal to 0, then this inner product is equal to 0. Do some substitutions, expand, and represent these terms using the two norm and inner product. finally you're going to obtain this result. So, and solve finally for the difference with respect to t. That's the way we obtain this result. And as I said before, this states that the Gibbs free energy is dissipated throughout time. About the numerical properties, so we're going to establish consistency, stability, and convergence. For consistency, we just compared this continuous operator with this discrete operator. And under suitable smoothness conditions on the solution and on the function f, it's easy to see that there is a constant c greater than or equal to 0, which is independent of h and tau, such that this inequality is satisfied at every grid point. So this states that the finite difference scheme is quadratically consistent, and the proof is done by using Taylor's theorem and the triangle inequality. In order to establish stability and convergence, we need a discrete version of Grunwald's inequality. This is the discrete version of Grunwald's inequality in this case. So this is Penhu's lemma. And also we need various calculations. We need some bounds, some inequalities, and some identities. I'm not going to go over the proofs because they're straightforward. So they're just some algebra. They require some algebra and also the mean value theorem. This is our theorem for stability. So under suitable conditions on A and F, if you have two solutions for the finite difference scheme and epsilon represents the difference between these two solutions, for tau sufficiently small, the difference, the k difference, is going to be bounded by this term. And as you can see, this is a constant. This is also going to be a constant, and this is the initial approximation. This is stability. Okay. And the proof for stability goes as follows. The first thing you have to do is to find the rule, the governing equations for epsilon. So these are the governing equations. They must satisfy these initial conditions. You take the inner product of this expression for epsilon with respect to this term. That's going to give you this result. Then you take the sum for k equal to 0 to n on both sides. You use telescopic sums, some algebraic simplifications, Young's inequality, Cauchy's inequality, and finally you obtain this chain of identities and inequalities. You move terms around and then you obtain the discrete form of Grunwald's inequality. So if you make omega equal to this term and rho equal to this term in Grunwald's inequality, then you finally obtain the conclusion, which is this one. Okay. So that's stability. And as a consequence of stability, we obtain the unique solubility. So under the same conditions, we establish that the finite difference scheme is uniquely solvable. Okay. The proof goes like as follows. And in the same way, we can establish the convergence of the scheme. So under suitable conditions, regularity conditions on U, on A and F, so we can prove that the system is convergent with quadratic order of convergence. I'm going to skip the proof because it's similar to stability. Finally, some simulations. So we're going to produce some simulations for A equal to 1, for F given this form. So these are snapshots at different times. There is another set of simulations. It's this one. And even in 2 dimensions. So for the 2-dimensional case, so we have this set of simulations. But more important than this is the behavior of the energy. So here we are plotting for those 3 cases the Gibbs free energy. And as you can see, this energy is dissipated throughout time. There were more simulations which are not presented in this presentation. For instance, we established numerically that the finite difference scheme is actually convergent with quadratic order of convergence. So as conclusions, we proposed a numerical model for a reaction diffusion partial differential equation. The equation considers a general value for the diffusion coefficient and general nonlinear reaction. And this result generalizes various known particular cases from the literature. So these finally are some references that we took for this study. And thank you for your attention.